Welcome back to the lecture. And in our last class, we discussed about the continuity equation. And first, we had discussed what the kinematic transport theorem is. And from that, we tried deriving the continuity equation. And we got the continuity equation for compressible and incompressible flow. So today what we'll be doing is we'll be exploring another equation, and after which we'll then try to see how many equations we have and what can we do with them. So the other equation which we are going to talk about is the kinematic transport theorem part 2, and from that we are going to derive the Euler's equation, which is kind of a second part of the momentum equation. So what I'm going to do now is let's directly take the kinematic transport theorem from here. So let me just copy this equation. Yes, I've copied it, and now we'll paste it here. All right. So here we have the kinematic transport theorem equation, and now what we're going to do is, so let's say that we are considering a flow, and let's say G, we have some property G. Let me choose a little smaller tip. Right. So let's say we have a property G, which is a fluid property per unit mass. Fluid property per unit mass. All right. And so of course, if this is a fluid property per unit mass, if we multiply that with the density, what we will get is fluid property per unit volume. So that is what we get. So we have G, which is a fluid property per unit mass, and rho G is fluid property per unit volume. So now what we'll do is, let's say we'll just actually input this rho G as f of xt, and let's see what result do we get. So we have d by dt triple integral rho G d volume, and this integral is over the material volume, and this equals to the triple integral dou by dou t rho G plus divergence of rho G, and this is the velocity. All right, dv. And if we expand this, what do we get? We will get vmt. This is actually understood now. By now we'll just solve it further and simplify things, and the final result will look something like this. All right, plus rho delta G by del T. It's all boring maybe, but yeah, we're just expanding and doing some calculations, replacing some terms. But of course, our main goal is to get the equation, which will be helpful to us. Okay, so we get something like this, expanding the whole thing mathematically. And if you remember from mass conservation, this is simply 0 d rho by dt plus rho v from continuity equation. In fact, we just derived that, and for now we are assuming that the flow is in fact incompressible, so this is 0. All right, from continuity. And so finally what do we have? So we finally have d by dt equals to d by dt triple integral rho G dv equals to triple integral full volume T into rho dg by dt dv. So I've just written out this term in terms of material derivative. This is the formula similar to material derivative which we had seen previously. So this is what we get, and this result is actually the let me just try and box that. Yeah, perfect. So this result is known as the second kinematic transport theorem. This is the second kinematic transport theorem. Okay, but okay, now this is not useful to us as of now. Like, what is G? You can input G as any fluid property per unit mass, then rho G will become any fluid property per unit volume, and then you can maybe use this equation to do something, right? So let's derive something useful from this second KTT. So take KTT, the kinematic transport theorems, as a tool which will help us to derive other useful equations. All right. So the next one, now what I'm going to do is I'm going to set this property G, which is an arbitrary fluid property per unit mass, and I'm going to say that G is nothing but it's the ith momentum. It's the ith momentum per unit mass. All right, so it's the ith momentum per unit mass, and let's say this is VI. All right, so ith momentum in the sense it will be the momentum in the x direction or the y direction or the z direction, right? So that's the ith momentum, and of course momentum is mass times velocity, so it's kind of a fluid property per unit mass because it involves mass as well. All right, then what we do is we put this in the equation. So what we are going to do is triple integral vmt fi plus dou ij by del xj dv. So here actually what I've done previously, I've put, so this is nothing but triple integral d by dt and rho and this property g d rho, and since you know that this is the ith momentum per unit mass, if I multiply that by density it becomes ith momentum per unit volume, right? So we are actually doing d by dt of momentum, that which is dp by dt, and previously we had seen above, yeah, so this is the equation. So d by dt triple integral rho vi dv equals to this equation. So instead of putting this again, I'm directly putting the right hand side of the equation. So moving down again, we have this in the right hand side. Let me change colors to pink again. So this is equal to d by dt triple integral rho vi dv, which is volumetric things, which is again equal to, so this we saw previously above, this is equal to rho dvi by dt dv. So this comes from the second kinematic transport theorem. So as you can see, this and these terms are both similar, so that is where it comes from, right? So we have this. So from this what can we write? From this we can write that rho dvi by dt, and if I expand this using the material derivative formula which we have, we'll have del vi by del t plus v dot gradient of vi is equal to fi plus dou ij by dou xj. So this is just the tensorial notation which I'm writing. So I've just said that if these two integrals are equal, then these two terms are also equal, because I'm integrating over the same material volume, and the the integral is also the same, so therefore they should be equal, and I've got this result. And this in fact is the Euler's equation. So this is the Euler's equation, which is well known in hydrodynamics, but this is tensorial form, and sometimes tensors can get a little scary, so we'll actually write down in the vectorial form as well. So vectorial form would be represented as rho d. Now as you can see, I've used this arrow, which means denoting that v is a vector, right? So by dt equals to rho del v by del t plus v dot gradient of velocity vector, and this I can actually write down as the force, which this force is the body force, plus gradient of tau. Now these tau comes from the viscous forces. So finally we have the Euler equations, which this is the tensorial form, so I'll actually write that down here. This is the tensorial form, and this is the vectorial form of the Euler's equation, and there you have it. So now this equation is what are the variables here? We don't know the velocity, because that's what we want to find out. Body forces we'll know, and we'll see what the body forces are in future videos as well. And there's something about the viscous forces as well, which we'll have to do some assumptions to make our problems easier. And finally, now we do have a bunch of tools and equations through which we can actually solve and get a whole mathematical equation which can describe the flow correctly. I wouldn't say accurately now, but correctly. So we have the Euler's equation, we have the continuity equation in our team, we have what more do we have? We have conservations of mass, which is in fact the continuity equation. We have the kinematic transport theorem, which won't be that useful. So we do have a lot of equations in our toolbox now. There's one more equation which we require, which will sum up all of them together. And once we have that equation in our team, we can then finally go about tackling how do we actually solve the problem. In fact, solving is just mathematics. We just need to figure out how to get all the equations for the number of variables which we have, which we look in the next lecture. Till then, stay safe and bye bye.